Welcome back. I'm not sure if you noticed, but you have to click on this. Well, now it's all glitchy, but it's a really cute hedgehog just going around. Anyways, that's important. I hope everyone had a good break. And I don't know why I put it off, but so it goes. I have laid out the remainder of the term. I mean, I am allowing for some kind of buffer days, but in general, we'll be on a pretty strict schedule. So today we're going to do section 5.1, and then tomorrow or next day we'll do section 5.2, blah, blah, blah. And then we're going to have quiz 2 on in the Friday block, right? And it's the same as quiz 1. It'll be open during the Friday block, but then of course you have all weekend to do it if the Friday block doesn't work for you. And so it's on chapters 4 and 5. And what I decided to do for the remaining chapters is, or the remaining quizzes rather, is just do a quiz per chapter because there's a lot of material in there. Okay, so 4 and 5. So we're gradually decreasing the amount of chapters in each quiz. Quiz 1 was chapters 1 through 3, and then 4 and 5, and then 6, and then 7, and then 8 you'll see on the final exam. So you'll see here, right, kind of regularly spaced quizzes now, and it's assuming kind of a quick pace. So hopefully you're reading along in the textbook. I know, add that to all the things that you have been meaning to do, right? And so quiz 2 will open on March 11th. Quiz 3 will open on March 25th. March is really long. I'm not sure if anyone's looked at the month of March on the calendar. It's 5 weeks exactly. So it's a really long month this year. Not longer than any other March, it just feels and looks like it. Oh yeah, so then quiz 3, March 25th is when it'll open, and then quiz 4 will open on April 8th, which leaves us just the last week to talk about regression. Now, I would love to spend more time on regression, but the thing is, if you need it, you'll see it in other courses, and it's really fun. So it's just kind of one of those quick to learn things because it is so fun. So that's why I'm kind of compressing it into that last week. It's unfortunate, but so it goes. And the final exam schedule, I haven't seen it posted. I haven't checked recently, but I'll let you know as soon as I hear any buzz. Okay. I saw a draft go around, but that's it. Okay. Okay. So where we ended before reading break was a really good kind of point to kind of leave that behind. We're not going to rely a ton on what we covered besides Z scores and the Z table and the Z distribution. So the normal distribution, that's pretty much all we're going to really rely on for future sections. And so today we're going to start to introduce this idea of sampling distributions. Okay. And what I decided to do is, because the textbook introduces some code to show you the idea behind a sampling distribution. And so I have a video because I have gone through it in the past, but in the interest of saving some time, I'm not going to do it this time, but I will post the video just so that you can watch it if you're interested. Okay, and so just well, let's start here. Welcome back. Hope you had a great break. And also I'll say quiz number 2 will open, oh, I said it and then I forgot when it was, so I'm just going to go back and check here. I'm only going to focus on quiz 2 on March 11th. We'll open March 11th. And it's the same as quiz 1, 50-minute timed quiz. Open all weekend. I'll put more details along with the quiz link. Okay. Just like quiz 1, I hope that I left some feedback as I went through the quiz. And so if, I was able to grab any information from your written work, then I made a note of that. Often they're just kind of notes to myself, not necessarily a note to you. So if it feels like I'm not really talking to you in the feedback, that might be true, right? It might be just for me as a reminder of what I was doing. But a lot of you will find that your written work was really helpful in getting you those some more marks, right? So that's why you should be submitting your written work for all the quizzes as well as the final exam. Okay? So I won't make it mandatory, but you should submit it just as a backup. Okay? All right, let's see. I can't remember chapter 5. So today we're going to start chapter 5, which is called Foundations for Inference. Now, okay, wait a second here. I can tell I didn't write anything over the break. Most of my stuff is typing, right? So when I do write after a week off, it's a complete mess, worse than usual. Okay, so foundations for inference. Well, let's talk about what inference is, first of all. Okay, so inference is the meat and potatoes of statistics. Okay, so when the reason you have to take statistics is so that you will be able to do inference. And so what that means is we take a sample, but the reason we take a sample is to try to learn about the population, right? And so we've talked about the importance of randomly sampling. And so our sample is representative of the population, right? So now we're kind of beyond that step. And so now the reason we need that so badly is because we need our sample to be representative so that we can infer something about the population and safely infer something about the population. Okay, and so inference is using sample information to infer something about the corresponding population information, about the corresponding population information. Okay. So what does that mean? Well, I could take, so our most basic measure is the mean, right? The average of something. So we take a sample and we calculate its average. And then what we're saying is, okay, I expect my sample average to be similar to my population average, but we also have a really good understanding of it won't be exactly the population average, right? I expect it to be close. And so that idea of, okay, well, I understand that there's variability in the sample information, right, in the potential sample that I collect, but I also expect it to be close to the population, right? And so that's what we're going to explore today. And so, for example, we take the sample mean, and maybe what I'll do is I'll bump this down and I'll label it. So we take a statistic, which is sample information. So this is a statistic. So using a statistic to infer something about the corresponding population information, well, that's going to be the parameter. Okay. And maybe not the, just parameter. Okay. And so, for example, we have the mean. Okay. And let's label this here. So the mean, X bar. Okay. We're trying to infer something about the parameter, which is our mu, right? So our population mean. Okay. And we introduced these a long time ago, but now we're kind of dredging them back up. Okay. And so we have this, the sample mean, so that's the statistic, and we're trying to infer something about the population mean. Okay. There are other statistics and parameters that we can consider. Okay. And so we can consider a difference in two means, right? And so now I have group 1 and group 2, and each of those have a mean, right? So the mean height of females versus the mean height of males, right? Now I have two separate groups, and so I have two sample means, and I can still compare these. Okay, so we're not going to use these quite yet, but it's nice to have seen them at least once. So x1 bar minus x2 bar helps us infer something about what? Well, the corresponding parameters would be the difference between mu1 and mu2. Okay. This is for numerical data. That's when we use the mean, right? And so if we have categorical data, then we usually talk about the proportion. And so our proportion statistic is p hat. Okay. And we're trying to infer something about p, or sometimes we'll use pi, just to stick with that Greek letter notation, right? But most of the time we'll just use p instead of pi. So that's where we stray from this Greek letter notation for parameters. Okay. But the idea stays the same. So the reason we avoid pi is because pi is an irrational number, right? So it kind of has other meanings, and so it doesn't really feel good to talk about pi in different contexts. So that's why we use p instead. Okay, but p hat is the sample proportion. Okay, and we're trying to use a sample proportion to learn about the population proportion. Okay. So here, mean or proportion. Okay. And just to highlight here, this is if we have numerical data. And I'm going to add one more to the proportion side, but this is if we have categorical data. There are many other kind of relationships that we can explore and analyze, right, and do inference about. But for now, let's just introduce these two key concepts. Okay. And so we can analyze the mean, or we can analyze the proportion. And just like we did for the difference in the means, we can analyze a difference in proportions. right? So P1 hat minus P2 hat is going to help us learn about the difference between P1 and P2. So proportions in group 1 and proportions in group 2, right? So especially if you're analyzing kind of website data, right? Google Analytics, that kind of thing, then how many page views resulted in a sale, right? They did or they didn't, that's categorical, right? And so now you can look at, okay, well, I had some proportion of page view, maybe sales on page 1 and some proportion of sales on, let's call them website 2 instead of page, because that might be confusing with the P's, right? And so then we can compare those, and then in that sense, we can compare the sales of the websites of 2 different websites. Okay. And so we can look at a comparison of more than 2 means or more than 2 proportions, but let's parking lot that for now. Okay, so one main thing is going to be identifying what type of question we have. Okay, and so in future chapters, in future chapters, it will be important to be able to identify what type of question we have. It will be important to first identify what type of question we have. Okay. So first off, is it a means question or a proportion question? And then is it going to be one mean compared to some number, or are we comparing 2 means to each other? Is it 1 proportion or 2 proportions? But for now, right, what we're going to focus on is just 1 sample proportion. Okay. And so, but in this chapter, we introduce the concepts using just the 1 sample proportion type of question. Okay, and so what's nice is the flow that we use and the ideas that we use for any type of inference question stays the same. So it doesn't really matter what type of question you have, okay, or what type of research question you want to answer. The methodology stays the same. Okay, and so we introduce these concepts using 1 type, and then in the future chapters, we'll just slowly pick through all these different types of questions, and we'll figure out what the differences are in how do we calculate a difference, for example, and stuff like that. Okay, so, but the ideas all stay the same. So in this chapter, we focus on 1 sample proportion, P hat, okay, to introduce the concepts behind inference. To introduce the concepts of inference. The methodology that we use for inference, and so it's kind of this umbrella term, okay, the methodology that we use stays the same regardless of the question type, right? Only slight changes have to be made. So the methodology there. Learned in this chapter, will be applied in all the remaining chapters. In all the remaining chapters. Okay. So we focus on this one type of problem. So you're going to feel very familiar with this one type of problem. But then when we start to introduce different types of problems, what's really nice is I'll be able to say, okay, only this changes and this changes in this scenario, right? Or, and there's only a limited number of things that can change. And it's a little bit early to talk about what changes, so that's why I'm having a hard time thinking about it. But let's just leave it there for now. Okay, and so inference involves confidence intervals and hypothesis testing. Confidence intervals and hypothesis testing. Okay, and so these are two main types of inference that we can use. And so what's really nice, right, is we're going to establish them with one sample proportion. How does it work with one sample proportion? What do we need to know before we can start? And then we'll look at what is a confidence interval and how do we interpret a confidence interval. And then we're going to establish the steps for hypothesis testing. And they are going to be what we use for all hypothesis tests. Now, hypothesis tests, we haven't talked about them, but that's where the money is, right? So if you want to say, okay, my vaccine that I've developed is significantly better than another vaccine, that would be a hypothesis test. The reason you're able to say it's significantly better is because it's statistically significantly better, right? And so that's where the money is if you want to prove something, okay? And then confidence intervals tell us, well, what is the difference, right? And so it gives us this interval of plausible differences. But I'm getting ahead of myself, and I will reiterate that once it comes back up, so don't worry. Let's start with section 5.1, and I brought this in from the textbook, and I'm gonna need a little bit more time before I can introduce it, but section 5.1 is called, I can never remember what it's called, point estimates and sampling variability. All right, so this idea of a point estimate is going to haunt us throughout the rest of the term now. Okay, so it's really important that we kind of think about it and talk about it. So what is a point estimate? A point estimate is the statistic. Okay. The statistic, which is a measurement from a sample. Measurement from a sample. Why do we call it a point estimate? Well, it's a point estimate. It's an estimate of something from the population, right? We're hoping that it's similar. right? Because we've applied our good sampling techniques. And so there's no reason to suspect that that our sample isn't representative of the population. And so now if I calculate the proportion of people who say yes to some answer or some question rather, then I have a point estimate for the entire population. Okay, so it's a point estimate for the population. Okay. So here we're going to focus on the proportion from one sample is denoted by p hat. So we already saw it, right? But now we're introducing it properly. And so the proportion from one sample is denoted by p hat. That hat looks weird there. Okay. And so it's denoted by p hat, and p hat is a point estimate. Maybe I'll do it, period. And p hat is a point estimate of p. Now, intuitively, we understand that our point estimate is going to change, right? We understand that if I took a completely different sample, even if it's a perfectly random sample, again, my p hat is going to be slightly different. Okay. So intuitively, we understand that we understand that p hat will change if we were to take another sample, a different sample. Okay, if we were to take a different sample. Okay. Even if both samples are randomly selected, and we can assume that they're both representative of the population, right? And so this is true even if both samples are randomly selected. And we can assume that they're both representative of the population. And we can assume they are both, we can assume they are both representative of the population, right? So this idea of, okay, that means that if I just look at one sample, I also understand that there are an infinite number of other samples that I could have selected of that same size from the population, right? And so what we're going to be able to establish is a sampling distribution for p hat. Okay, and so the collection of all the possible p hats results in a sampling distribution for p hat. So the collection of all the possible p hats results in the sampling distribution of p hat results in the sampling distribution of p hat. I'm going to bump this guy down more. So this is what we're going to focus on today, is the sampling distribution of p hat. And this is where in the textbook there's a chunk of code that you can run, and I'll post the code on our Moodle page in case you wanted to play around with it. And so you can, but I'm skipping it. I might regret it. It's pretty fun. But the code is there and you can play around with it. And it just shows how you would develop. So it pretends that you have a population. And so you're generating values that mimic that population, or kind of random samples from that population. And then we look at the distribution of the p hats. And what's really, really cool is the sampling distribution of p hat stays the same. It just hinges on the sample size. Okay. And so one thing I wanted to say before we go on is the error between our point estimate and our parameter is just the difference between the two. Okay? So the error is the difference between the point estimate, which in this case is p hat, but it's true for any point estimate, right? There is the difference between the point estimate p hat and the parameter. And the parameter we're talking about now is p. Sorry, I almost put a hat on there. Okay. And so this error it can come from two separate places, right? It can come from just sampling error, right? So that idea of, okay, well, if I took a different sample, then I would have a different p hat, right? So that would be the difference, okay? Or it can come from bias, okay? And now bias, there's really nothing we can do about it after we've just tried to collect a random sample. And so once we've collected a random sample and we're confident that we have a representative sample, then we assume that the bias has been minimized at least. Okay. So the error comes from two separate places. So the error comes from two different sources, let's say. First off is the sampling error. Okay. Now the sampling error, right? If I take a sample of size 10, right? And then I put those guys back into the population, and then I collect another random sample of size 10, then the difference between these two random samples of size 10, so a small sample size, can be quite large, right? And so what we do is we try to minimize that and say, okay, well, if I collect a random sample, then what I would expect is that my the difference between these two groups, or my random samples, will be smaller, right? Because I'm taking up more of the population each time. Okay, and so the sampling error we try to minimize by increasing the sample size. And I'll show you why once we have a formula to look at. Okay, and the other one is through bias. So bias is the tendency to select certain observations into your sample, or kind of the wording of questions. So that's introducing bias. So it goes back to, I think it's chapter 1 or chapter 2, where we talk about proper data collection techniques, right? And so that's to minimize the bias. And we try to minimize the bias by using proper sampling techniques. By using proper sampling techniques. Good. Okay. So we've got this idea of, okay, well, I've collected one sample, but that's just one potential sample. Even if I've randomly selected everything and everything is all, you know, we can assume it's representative of the population. Even then, I could collect an infinite number of samples just like that, same size, everything, right? And so what we have done traditionally in statistics is we've established these sampling distributions. And what's really nice is they've been established for many different kinds of point estimates. Now, what you'll find if you go on to Stat 240 is that in data science specifically, we kind of have moved away from this traditional sense of, okay, well, p hat follows this distribution and I know what it looks like, and so I know how to calculate these things, into kind of a more computer heavy version, which doesn't rely on sampling distributions anymore, right? But we still use them, and so we do need to know what they are and what they look like. But just be aware that in data science, you'll move away from these things, but they'll happen naturally anyways. So the central limit theorem is a really important concept. And so here, I'm going to highlight it here. Okay, so the central limit theorem is as important as it sounds. Okay, so here I'll say as important as it sounds. All right, central limit theorem. Don't worry if you've taken calculus, there's no limits here, although kind of there are, but not that we need to care about. Okay, and so the central limit theorem is this really very cool thing that says that, okay, as long as you can assume that your observations are independent and your sample size is sufficiently large. So those are the conditions that we need to satisfy before we can apply the central limit theorem. But once we've checked those, and I'll show you how to do that, then what we're going to say is that the sample proportion p hat, okay, so that point estimate that we've collected, will tend to follow a normal distribution. That's crazy. With a mean of p and a standard error of p hat. or sorry, a standard error, and then a little subscript p hat to denote that it's the standard error for p hat. Okay. So we're going to talk about the central limit theorem and what that means for us, right? But we're going to pick this thing apart. And where do we start? Well, let's start with the conditions. Okay. And so when observations are independent, okay, the only way, or kind of the main way that we check that, is to make sure that we have a randomly selected sample. Okay. So maybe what I'll do is I'll kind of copy and paste, and then I want to talk about when observations are independent, okay, which means we need to have a randomly selected sample or at least be able to argue that the observations are independent, or at least be able to argue that observations are independent. Okay. And maybe what else? I'll label this the conditions first. Okay. There. So the independence portion of the central limit theorem, in this case for p hat, is kind of vague, and it usually will be. Usually we can just say, okay, well, this sample was randomly selected, or I assume it was randomly selected, so I can assume that the observations are independent, right? So the independence assumption check is pretty easy. And the sample size is sufficiently large. That's our second condition. Okay. Okay. Now, how can we decide if the sample size is sufficiently large? Well, that's when we kind of drop down to the bottom of this here, and we have this success failure condition. We've seen this success failure condition when we use the normal approximation to the binomial, right? And so we've seen this idea before. Okay. And so we've seen this before. We have seen this in the assumptions for the normal approximation to the binomial. It's kind of entangled, and it's not something that I expect out of you in this course, but they are definitely related, right? We have some proportion, so some sample proportion, which is the same as the probability of success in a binomial situation, right? And so it's very, very similar. And so that it makes sense that we have the same conditions or assumptions that we need to check. Okay, and so maybe I'll kind of add that here, conditions / assumptions. There. Okay. And so the sample size is sufficiently large. How we check that is we check that n times p is greater than or equal to 10, and n times q, or 1 minus p, is greater than or equal to 10. So this means that we have to have at least 10 successes and at least 10 failures, and that's why it's called the success failure condition. Okay. Now, what we're going to come upon is, well, the whole point was to use p hat to learn something about p, which means that I don't actually know what p is. Okay. And so notice in inference, we're trying to learn what p is. Notice in inference, we are trying to learn about p, right? The parameter. So we won't have a number for it. Okay? So we do not know what it is. What it is. So unless we know or have some hypothesized value of p, then we use p hat in its place. Okay, so unless we have a hypothesized value of p, oops. The reason I'm highlighting that unless this is true, right? Unless we have some hypothesized value, and just knowing that hypothesis testing is coming up, potentially not knowing anything about it, right? You can see that there will be a scenario where, okay, I'm going to have a hypothesized p, so then I would use that instead of the p hat. So unless we have a hypothesized value of p, we use, oops. We use p hat in its place, right? Because p hat is a point estimate of p. We use p hat in its place. And I see this of, and I can't read it, so I'll have to fix it. Okay, so I'm going to highlight this because that's going to come up, right? And it can be confusing in the beginning to remember when you can use the p or when you can use a p hat. But basically, if you have a p or a hypothesized p, you should use that. If you don't, which we're going to start off with, you use p hat instead. Okay. So what that means is we would check, therefore, we would check n times p hat has to be greater than or equal to 10, and n times 1 minus p hat, which is n times q hat, has to be greater than or equal to 10. This is the same as the observed number of successes and the observed number of failures. So this is the observed number of successes, and this is the observed number of failures. And hence it's called the success failure condition. Okay. You don't need to call it the success failure condition, but if you read something and it mentions the success failure condition, then this is what it means, right? And I know that jumping between p and p hat is really, really confusing in the beginning. But for now, what we're going to use is just p hat instead of p. So whenever you see a p, you have to use p hat because we don't know what p is. Okay. So now we've talked about when observations are independent. That's kind of the easiest part of being able to use the central limit theorem. And then the sample size is sufficiently large. We've already done it, so it's actually not that bad. So then what this portion says is the sample proportion p hat will tend to follow a normal distribution with a mean of p and a standard error of the root of p times 1 minus p over n. Okay, and so here, let's see here. I'll start on a fresh page here. If the above conditions are satisfied, we are allowed to assume, or we may assume that and what I'm going to do is I'm going to cross out. We may assume that the sample proportion p hat will tend to follow a normal distribution. So let's start out and say, okay, well, that means that p hat, and how do we denote it follows a normal distribution? Well, we use that tilde. So we use the tilde follows and just as a reminder here, right, that tilde means follows and for a normal distribution, we use a capital N. And so here, a normal distribution with a mean of p. Okay, so notice the little subscript mu p hat is p. It just means that the center of all these hypothetical p hats that we could generate, right? We won't, we'll only look at one, but the sampling distribution of p hat, it will be centered on the population proportion, right? Which makes sense, right? We expect all our sample proportions to be close to our population proportion. And so eventually what we'll see is this normal distribution start to develop and it'll be centered on the population proportion. Okay? And so we use these little subscripts here because later on what we're going to have is we're going to have some sampling distribution for the difference in proportions, for a mean, for a difference in means. And so, but the idea stays the same. Okay. And so it's going to be centered on P, and the spread or the standard deviation is P, the root of P times 1 minus P over N. Yeah. So notice that this is the spread of P hat. Gets a little bit confusing, right? Because we usually use this as a spot to write our standard deviation, right? Later on, what we're going to see in the problem is that the standard deviation is going to be different from the standard error, because the standard error takes into account that, okay, all these sample proportions will be closer together than a single proportion, okay? And so, or than individual proportions, okay? So this is what we call the standard error of P hat. Okay. So every point estimate is going to have some standard error, right? Some spread associated with it. Okay. So every point estimate will have its own standard error. Okay. Will have its own standard error, which will be a measure of spread in the sample or in the point estimates, which will be a measure of spread in the point estimates. So I know that this is a weird concept, especially in the beginning, is this idea of, okay, well, in theory, I could have selected any random sample, so let's fix our sample size 100. And let's say I'm drawing from a population of Canadians. And so my population is all Canadians, and I want to use a sample of size 100, or I could increase it 1,000, 20,000, whatever. But let's focus on 1,000. So then I could randomly select a sample of size 1,000, and I could calculate the proportion of something, right? Who has a landline at home, right? It's a yes or no answer. Do you have a landline at home? Yes or no? And so the results would be a proportion of people who have a landline at home, or depending on what I'm interested in, right? Very similar to the binomial situation. If I'm interested in the proportion of people who do not have landlines at home, then that would be a success, right? So depending on what I'm interested in, I would denote that as my success, my p hat. Okay, and so I can collect a random sample of 1,000 Canadians, and I can ask them and figure out what proportion of those Canadians, of those 1,000 Canadians, have a landline at home, right? And so I guess a landline would be at home, kind of redundant, but anyways, and so there's nothing stopping me from putting those people back into the population and then collecting another random sample of size 1,000, and I would have a slightly different sample proportion of people who have a landline at home. But eventually, if I collect enough samples, then they're going to stabilize and they're going to form this normal distribution with a mean of p, which is the population proportion, and a spread of this root of p times 1 minus p over n. Okay, and so so every point estimate is going to have some spread, because we understand that if I collect a different random sample, I'm going to have some variability in my estimates. And so every point estimate is going to have this some sampling distribution. Okay? And so this is what we call the sampling distribution. The sampling distribution of p hat. Okay. Okay. And again, right, if I have to use the spread, so the standard error, I don't have a p, right, because I don't know what it is. I'm trying to learn what it is, right? So just as in the conditions, because I don't know p, we use p hat as our best guess at what it might be. Okay. So I'll just reiterate. So as we did in our conditions, we use p hat in place of p, since we don't know what p is. we use p hat in the place of p, since we do not know what p is. So what that means is that the spread that we're going to use is, so in practice, therefore in practice, the standard error of p hat is going to be approximated by, so I'll use approximately equal to the root of p hat times 1 minus p hat over n. Okay. And then of course it's going to be centered on our p hat, but we'll leave that alone for a little bit because it's less important. And so here, notice what happens is, okay, I have p hat, so I have some sample proportion, and oh, my computer is threatening to die here. Let me just plug it in. Everything is kind of, there we go. Okay, good. What's I saying? Anyways, oh yeah, so the spread of our p hat, right? If we think about, okay, if I take a sample of 10 Canadians and I ask how many of you have a landline at home, I would get some proportion, let's say 4% or 0.04, right? And so, whereas if I take another random sample of 10, then maybe 6 people out of 10 have a landline. And so we're assuming that there would be quite a lot of variation in the different sample sizes. Whereas if I increase it and I talk to, 10,000 Canadians and I ask them how many people have a landline at home, then I'm going to see this kind of less variability in my p hats, right? Because I've considered a larger sample size. So here, how that's reflected in the formula for our spread, remember the standard error is now our measure of spread, okay? And so how that's reflected is by this n in the denominator. Notice that as I increase n, right, I'm dividing by a larger number, okay? And so that means that this whole value inside the square root is going to decrease, right? Think about 10 divided by 2 versus 10 divided by 8, right? That kind of thing. So as I increase the denominator, what I'm dividing by, I'm going to get a smaller number. And so as n increases, the standard error is going to be decreasing. So notice, as n increases, the standard error of p hat will decrease, right? Which means that the variability between the sample proportions will decrease, right? The variability between samples will decrease. Okay. So what the central limit theorem says is that, okay, if I have checked that these conditions are satisfied, then I can go ahead and assume that it follows this normal distribution with a mean of p and a standard error of p hat times 1 minus p over n. And so let me just make sure I'm not skipping anything here. So I feel like I had something else that I wanted to say. Okay, that's okay. Okay, so the central limit theorem, I guess I shouldn't use the abbreviation until I've defined it, but we usually just abbreviate the central limit theorem as a CLT. So the central limit theorem the central limit theorem, the CLT, says that if you have collected a sample, a random sample, so as long as the conditions are satisfied, the central limit theorem says that as long as the conditions are satisfied, which means that I have independence, which in this case is going to be a randomly selected sample, allows us to kind of check that condition. So a randomly selected sample. Then I can assume normality by the success failure condition. Which means I have to check that NP hat is greater than or equal to 10 and NQ hat is greater than or equal to 10. Yeah. So as long as those conditions are satisfied, and this is where I want to introduce an optional condition that we sometimes introduce, and I've emphasized it more in the past. And so the reason I'm bringing it up is because it's part of those extra practice problems that I posted at the bottom of our Moodle page. And so if you see it, then I don't want you to be thrown off by it. But it is kind of optional because it's pretty rare that it's an issue. But an optional condition is the 10% condition. And I'll bump that down here. The 10% condition says that your sample size, it has to be large enough for at least 10 successes and at least 10 failures. But the 10% condition says that, well, your sample size has to be large enough, but not too large. It can't be larger than 10% of the population. That's rarely ever the case, right? That you're going to have a sample size that's larger than 10% of the population. But the reason for that is, the reason it becomes an issue is because it messes with the independence, right? Even if you have randomly selected your sample, then if you're collecting a huge part of the population, you're going to introduce some dependent observations. Okay, and so the 10% condition says that our sample size should not be more than 10% of the population. So it should be large, but not too large is kind of the idea. So it should not be more than 10% of the population, since it would introduce dependent observations into our sample. So it's part of that independence condition. So optional, and maybe I'll add in here, optional independence. Oh, helps if I write the whole word, independence. Okay, just want to have that in there. Okay. But what this says is that, okay, if these conditions are satisfied, then what I can do is I can say, okay, then let's see how I wrote it. The CLT says that as long as the conditions are satisfied, we can assume that P hat comes from a normal distribution centered on P, which we're going to swap to P hat, but that's okay. And a standard error of P times 1 minus P over N, which means that it would come from this theoretical distribution centered on P with a spread of roughly P hat times 1 minus P hat over N. So now, as soon as we see this normal distribution, right, and I know where it's centered and I know the spread, right, then I can go ahead and I can leverage those Z-score calculations that we've used in the past. And so this means we can leverage the Z-score calculations and the distribution that we covered earlier. This means we can leverage the Z-score calculation to find areas under the curve which are probabilities. Yeah. One last thing that I wanted to note before I let you go is that let's think about the success failure condition. Yeah. The reason it's 10 is just to make sure that you have a large enough sample. Now, if P hat, if the sample proportion that you're trying to detect or that you're looking at is close to 50-50, then it's really easy to get a large enough sample size where the success failure condition is satisfied, right? Because then if you have a P hat of 0.5, then you would just need a sample size of 20 and the success failure condition would be satisfied. But what if you have a P hat that's really, really, really small? So something that's very difficult to detect. So when I worked in as a data analyst, we were looking at attrition data at a credit union. Yeah. It was First West Credit Union. But anyways, and so attrition data is who's closing their accounts and how can we pick up on those people before they close their accounts. And so that's really hard to do, right? Because the proportion of people who close their accounts is very, very small compared to the people who don't, right? So then you would need a very, very large sample in order to be able to pick up on those proportions and to be able to do inference on those proportions, right? And so so the sample size that you need is going to depend on what proportion are you trying to pick up on, right? If it's close to 50-50, then you don't need a very large sample size. But the further you get from 50%, I guess in theory in either direction, because it's a success failure condition, then you need to increase your sample size, right? So let's see here. So what we're going to do next day is we're going to pick up with this idea of, okay, I have a normal distribution. So that means I can calculate Z-scores and I can find areas under the curve and I can find probabilities, which we already know how to do, right? And so we're going to pick up with that and start talking about confidence intervals next day. If you have any questions, let me know. but I'll stop this recording. I'll see you next time.